So, hello, Professor. Blue, sir.
Yes. Oh.
So, let's start the class. We have a.
Okay, so we can start now, right? Yeah. Okay, so today we are going to look into biomedical application of CN, specifically some biomedical CN models. So these models are typically applied to various problems. I think the most famous one, all of you, at least some of you already know, which is the protein structure prediction, 3D structure prediction, AlphaFold. So we are going to look into how AlphaFold architecture is developed. So we start from the fundamentals of biology. So perhaps most of you have already known a protein is a long chain of amino acids, polypeptide. So it's just like a strand of beads connected one after another. So there are 20 different kinds of beads. They can be colored differently as illustrated here. So because each bead there are 20 kinds of them, right? So each bead has specific physical chemical properties, and those properties actually define the interaction among the beads, and then eventually they fold into some kind of 3D structure. So the task of an AI like AlphaFold is the prediction based on the starting from the sequence, the amino acid code, the alphabetical codes on the top, and then the task is to predict the folded structure of the protein. So if we look into the amino acid, each bead, we know that it has a special type of structure centered around a carbon called alpha carbon. And then, so there are certain chemical units connected to the alpha carbon, particularly NH2 unit and the COH unit, and also this R unit. R is actually a symbol for 20 different kinds of units. So that defines the specific amino acids. So here are the structures of the 20 different amino acids. You see the alpha carbon here, and then the COOH, and then NH2 here. So sorry, alpha carbon here, and the COOH, and the NH is here, and then this is the side chain structures. So because of the physical chemical properties of those beads, those amino acids, they tend to form some kind of predictable interactions among the amino acids. So if it forms this kind of hydrogen bonding scheme, so the local chain actually folds into a alpha helix structure. So this is called a secondary structure. That is the local folding pattern, defines the local folding pattern. But because of the general flexibility of the long amino acid chain, so it typically folds into a globular type of structure called tertiary structures. And then different chains may actually combine, form a multi domain structures called quaternary structures. So of course, the quaternary structures make the structural prediction even harder. But at least AlphaFold is capable of predicting the tertiary structure with quite a good performance. So the question is how a amino acid chain fold into a globular type of structures. That is because of the flexibility of the chains, the chemical bonds surrounding the alpha carbon here, the alpha carbon here. And you can see that the chemical units on top and on the bottom of the alpha carbon, you can see they can actually rotate along this chemical bond connecting the alpha carbon with the next unit. So the next unit actually almost forms a plane. You can almost assume this plane is kind of rigid structure that can somehow have a certain degree of freedom to rotate along the chemical bond connecting the unit with the alpha carbon. These angles are called the torsion angles because it can rotate with a certain rotational degree, right? There are two chemical bonds, rotatable chemical bonds here. So there are two rotatable angles, torsion angles. One is phi, the other is psi, phi-psi angles. Of course, there are additional angles which may so actually the surrounding unit may not necessarily to be a totally rigid structure. So there are additional rotational angles, but those angles typically you can assume the variation is relatively small. You can assume it's almost a rigid type of structure. So based on this definition, of course, we can use because typically we know the range of the length of the chemical bonds. We know the range of the angles between the chemical bonds if we assume they are somehow rigid. So that leaves only two flexibility phi-psi angles. So by using this kind of geometry and then coupled with mathematical formulation for rotation of the rigid body, you can actually theoretically construct a folded chain based on the variation of the phi-psi angles. So there are a whole theory of statistical theory about the range of phi-psi angles in different protein structures. If you are interested in that, if you have not learned that, I recommend you to read some molecular biology textbooks or biochemistry textbook where there are more detailed discussion about this. So anyway, we can see that based on the structural consideration of the amino acid chain, the polypeptide chain, the protein chain, and based on the simple mathematics here, we can imagine that we can have some formulation built or some variables built into the each amino acid because each amino acid is supposed to have a phi-psi angle along with that. That defines its positioning, its orientation along the polypeptide chain. So this is some basic understanding of biology, molecular biology of protein structures. Based on that knowledge, and now we can look at how we can develop an AI to predict that fold. AI also has to start with a amino acid chain, the alphabetic letter. We know that we already mentioned that. Associated with each amino acid, there are these so-called phi-psi angles, other variables, and the different side chains with different physical chemical properties. So those properties could be presented as a kind of vector called the local descriptors. Each descriptor vector, just as the longitudinal box here are showing here. So each vector represents the local properties or local descriptors of the alphabetic letters, the specific amino acid. So this is the description. But we know that the protein folding is more than, much more than the localized, isolated amino acid properties. There's interactions. For instance, we know that based on the protein structures here, we know that the nearby residues, the nearby amino acids, even though they may be far apart from the sequence-wise, but the distance-wise, they may be close enough to have local interactions, like a hydrogen bonding, like hydrophobic interactions, and so on and so forth, right? So these kind of interactions should be described by another set of descriptors, another set of representations called global descriptors. So in order to fully describe the features of a protein, you must have local descriptors, the local features for each amino acids along the protein chain. You should also have a global descriptors that can actually reflect the folded interaction among the nearby and the distant amino acid, right? So this is what we can understand based on the molecular biology of the system. But the question is how we can develop the specific global descriptors. So before we touch that, we first look at the easier ones, the local the descriptors. That can be quite simple, right? So each amino acid must have a certain kind of properties, be it physical chemical properties, be it evolutionary properties, any kind of property you can all the properties associated with its typical range of the second the tendency to form a particular type of secondary structures with particular type of phi psi angles and so on and so forth. Actually, you can include all of them here. So one of them is the evolutionary properties of each amino acid. By evolution, we know that evolution means sequence variation, right? Sequence variation means the mutations, insertions, deletions, and along the protein chain, right? So these kind of things is equivalent to the substitution. So the equivalent to the question of which amino acid can be which amino acid can be utilized to substitute this particular amino acid without changing the function of the protein. So this is called substitution. So that means you can form a substitution vector, a score. So give a score of the other 19 amino acids. So you can have a 19-dimensional vector, each with the so for each amino acid you have the other 19, and then each with a score showing whether or not that amino acid can replace this amino acid. That means or this amino acid can be mutated into the other amino acid without changing the protein function. So this is the so-called substitution matrix, widely utilized in protein structure deep learning models, particularly AlphaFold. So now we look at the general feature of a local descriptor. So in the beginning, we have a protein sequence, alphabetic letter of a certain length, length n, for instance, sequence length n, and then each amino acid has a vector representing the local features, maybe with M. So this forms an N by M matrix. So there are different ways uh, to actually develop the features for AI to learn. So one possibility is to you simply extend so you essentially you construct a single vector which a particular each section representing the local property of each amino acid. So this that means this yellow colored one represents the first represent this amino acid, and then the next one represents the next amino acid, and so on and so forth. Each maybe with the length of m, and then you form a super long vector to represent the whole sequence. So that's one way to represent the protein. Alternatively, you can use UMAP to reduce the dimensionality of n by m into a lower dimensional, for instance, m-dimensional variables. So that's also a possibility. Of course, you can keep the whole matrix on retain the whole matrix, and then you just have this n by m matrix. So there are three ways to form a representation of a protein. So that's the local descriptors. What about the global descriptors? The global descriptors are a bit complicated. Suppose that we know the protein must form some kind of folded structure. Then we know some remote amino acids, they are actually close to each other. So you can actually develop a so-called distance matrix reflecting the pairwise distance between the uh, amino acids along the so irrespective of whether or not they are close or they are far apart sequence wise. So you can develop this kind of uh, matrix. So this matrix is something like this. So you start with the first amino acid, and then you can list all the amino acids that can potentially be close to this particular amino acid, and then you form some kind of matrix. Of course, you have always have these questions. Suppose we do not have the prior knowledge of the protein structure. How do we know the distance? So typically, just like in many other cases, for instance, in the case of k-means, we also don't know what is the center of each cluster, right? So suppose we have a k cluster, and then we have to randomly assume. So this is a similar thing. So we may have to start with a randomized distance matrix, but actually in reality we don't have to, because we already have plenty of knowledge about the known protein structures. So typically we start from some known protein structures as close as to our new protein sequence. So that's the actually the more practical approach, rather than starting from a randomized distance matrix. Okay, so once we have this initial inter-residue distance matrix, and then we can train our deep learning models to gradually refine, to gradually improve the distance matrix, and then until it match to the correct answer. So that's called the training process. So essentially, all the AI models actually they are tasked to eventually reproduce the good the right solution during this training process. So this is the thing. Okay, to summarize, we have many different prior knowledge for generating the local and the global descriptors. So some of them are listed here. Actually, some of them are utilized by AlphaFold and many other structural prediction deep learning models, including position-specific scoring matrix, that is some kind of substitution matrix, including the pairwise distance between the any type of alpha carbons. So these are the good start for you to generate the initial matrix, the local and the global matrix. Once you have that, you are ready to construct deep learning model, but we have to so when you develop deep learning model, we have to have what is the task of each deep learning model. It could be the prediction of the function of the protein based on the sequence, input sequence, or based on the input structure, or it could simply be the prediction of the structure based on the input of the sequence. But it could also be the protein design. In the protein design, we don't have a predetermined sequence because the sequence is the one we want to design. So typically we start with some kind of functionality, desired functionality we wish to eventually achieve, and then we have to apply certain models to actually generate the kind of sequence. Because we mentioned we have local distributed matrix, N by M, N matrix, we have pairwise distance matrix. So those matrices, they are not really too different from an image, which is actually a pixel of, actually a matrix of pixels, right? So essentially you can apply CNN. So that's why after only after the last lecture of CNN model, we quickly jump into the applications, particularly the protein structure prediction, because you can actually apply CNN for protein structure prediction based on the input of local descriptor matrix and the global descriptor, essentially the pairwise distance matrix. But CNN is not the only method applied for protein structure prediction. So before these few years, actually, people applied RNN, autoencoder, generative adversarial networks. So some of them we are going to study in the subsequent lectures. But here we just focus on the CNN. But we let you know that there are other, and also in the in these few years, transformer has also been applied for protein structure prediction. So essentially, it doesn't have to be just the same. You can apply many different AI architectures. Okay, so anyway, we focus on protein structure prediction based on CNN. So if we compress the sequence feature into a long vector, one-dimensional vector, you can just apply one-dimensional CNN. So for instance, 1D ResNet. So here when we talk about a scene, so typically there are different architecture of a scene, each with a specific name, like here ResNet, maybe, and also soon we are also going to look into UNet and other networks with a specific name. So actually each name actually correspond to a particular architecture, particular structure, we actually do not go into these because there are quite a number of them, ResNet, InceptionNet, UNet, and there are quite a number of them. So anyway, I think for us, because all of these networks, they have open source codes. So for you, even if you don't know the details of the structures, at least you know the principle. They are thin models. So for you as an application, as a person with with biomedical application in mind, so you don't have to know the details of the structure in order to use the source code, use the code. You can directly use the code, but at least you need to know the fundamentals of CN. And if you are really into it, so I highly recommend you to spend some time to read specific models, read the information about specific models. Here we actually do not go into each model because of the nature of our lecture and because of the time constraint. Anyway, so if we start with the pairwise global feature, and we could use a 2D CN models, 2D CN models, or if we have a 3D, it can also be depending on how you treat each layer of the information, each layer of the 2D matrix. So essentially, there's this multi-channel 2D CN models which you can apply to actually eventually derive the true distance among the alpha carbon for to succeed in generating the protein folding structure. So just like actually, how do we evaluate whenever we talk about the AI model, we always need to have some kind of judgment of the performance of the model, right? So we have to have that. And how do we judge? So we talk about the sensitivity, specificity, those kind of performance measures, but those are actually for the prediction of the certain variable values of prediction certain nature like inhibitors and non-inhibitors, certain class labels. But for protein structure prediction, it is more complicated. So that's why people define the certain scores called the TM score, TM score. So it is based on a program alignment protein. That's not necessarily protein. It's just a structural alignment program called the TM align. So it has a pretty much defined score to judge the performance of predict structure against the standard structure. So essentially, when you read about the performance comparison of structural prediction AI, typically you see this kind of tables or figures showing the TM scores. So at least you need to know what TM score is. So again, I do not go into technical mathematical details of the specific algorithm. I just give you this some kind of lead. So if you are interested in that, you can follow the lead. You can search this TM align, and then you can get the detailed description about this TM score, how they defined it, and what's the mathematical reasoning for for this kind of formula. Anyway, so when you read about the performance, and at least you should not be unfamiliar with the terminology TM score. But for us, for instance, AlphaFold 2, now it's AlphaFold 3 already. AlphaFold 2 has a performance around 90. It's like 90% or something like that. So we need to know, is this performance good at what level? 90% or 90 score, how good it is. So essentially, a score, if a score is above 90, TM score is above 90, it is roughly equivalent to the experimentally determined protein structure. So once it reaches that level, it can compete with experiment. So that's the level of performance. So you can see that AI is really reached to that has reached to that level. So essentially, okay. So now we look at a specific example of AI architecture. We take AlphaFold 2 as an example. So of course, the starting point is this sequence, and then we should have a neural network to be able to predict a distance matrix and also to predict the phi psi angle. And utilize these two information, we need to be able to generate some kind of protein structure. So that's the typical workflow, starting from the sequence, going through a network, and then it is able to deliver a distance matrix, a phi psi angle prediction, and then eventually it leads to the structure for you. So the question is how it can go through that to give you the phi psi angle and give you the distance matrix. So essentially, the starting point, as I mentioned, it is a sequence, and then we can utilize the vectors along the sequence. The vectors could be substitution matrix, could be many other things. Some of them I have already mentioned. And then through that, we can generate this kind of residue phi psi angle matrix and residue distance matrix, two matrices. Of course, phi psi and the distance, they are actually interrelated, so you have to synchronize, so update one by another to make them consistent. So it is some kind of iterative process, one improving the other, and then it's kind of is and then one improving the other, and then the other improved the one. So this kind of process, vice versa. I forgot that English word, and then vice versa. Okay, in this particular case, the local distributor is represented by the MSA, which is the substitution matrix. You represent that, and then you have this pairwise distance matrix, and then it goes in this iterative process to update one another until it reaches the final two matrices. And then based on these final two matrices, that means we have the phi psi angles, we have the inter-residue distances. So based on these two, actually, and then based on our, remember that initially we talked about, we fix the units near the alpha carbon as if they are a rigid structures. the on a plane. So and then we can use this geometrical model to generate the fold. So this is the fold structure. And then we added the amino acid side chains, the alpha, the R groups. We added the R group back, and then we employ some other molecular modeling strategies like a molecular dynamic simulation or whatever to optimize a structure. And then we arrive at this final structure, and then we compare with the standard answer from experiments to see whether it is satisfactory. If it is not, then we have to start another round of training process until we reach a satisfactory result regarding the predicted structure. So that's the whole process. So here you can see some description about the use of gradient descent. So these are the typical molecular modeling methods. So again, we are not going to go into details of the molecular modeling. So if you are interested in that, I think you can actually find out the material, the textbooks materials regarding to the molecular modeling methods. So anyway, based on the molecular methods, we can generate a different kind of protein structures, and then can look into the improvement of the TM score. We want the TM score to be improved. Apart from TM score, there are also other scoring like RMSD. So we may revisit it sometime. So at least we already talked about TM score. So look back on the AI side. So because we start from the two matrix, we can treat them as some kind of image, and then we can apply convolutional neural networks. Particularly in AlphaFold, they utilize ResNet scene architecture to actually learn from the initial matrix in order to produce this distance or phi-psi matrix. So that's the process. So essentially, as I mentioned that, so after this scene run, either it is it is a scene, it is a ResNet or any other scene. So eventually, this ResNet or scene model actually gives you two matrices, right? Two matrices, torsion angles, phi-psi angles, and also distance matrix, right? And then starting, so this is a more detailed architecture of the ResNet model. So this is the activation function. So this is the batch normalization. So you can see that because it runs so many runs, so it frequently use normalization to ensure data is not deviated away from the true value. And then you have this kind of convolution process, these kind of things. So after you get this matrix, and then you know the angles, you know the geometries, but geometry is not the only factor to determine the fold of a protein, because these amino acid residues, they have interactions between them. Interactions, it is essentially it is physical chemical interactions defined by the laws of physics. So that's why you have these van der Waals interaction parameters input into the system, and then you need to calculate the potential. Potential is a concept of physics describing the interactions of objects. So the potentials, they are dependent on the structure elements of the protein fold, particularly five side angles, and so on and so forth. In this way, because we have the initial five side angles based on the previous knowledge, and because we have so many structures to train our systems, eventually we can, and then we apply the molecular modeling method, gradient descent method to optimize our 3D structure eventually, and then we can do this in loops. Eventually, we get the correct the final answer. Because of the complexity of the problem, our scene model, so actually not our, the AlphaFold, the scene model AlphaFold 2 is actually quite complicated. It's not a simple ResNet model. It's a more complicated model. So some details are given here. Actually, by the time I designed this PPT almost 2 years ago, so we do not have detailed information about AlphaFold 2 structures. I don't know whether now we have or not, and so I leave it as some kind of homework for you. If you are interested in AlphaFold 2, you can search the detailed scene architecture of the AlphaFold 2. Here is just peak of part of it, some of the information. AlphaFold 2, as I mentioned, at least it is superior than any previous models, including AlphaFold. So here is the comparison of the model performance. You can see that almost 10 years ago, so the performance AI in predicting protein structure is only around 40. Only after AlphaFold, it increased over 50, close to 60%, 60, and then AlphaFold 2, it reached almost 90. So here is a comparison of AlphaFold. So this is all the table I got from a Nature journal paper. You can see AlphaFold, the performance of AlphaFold in comparison with some other deep learning models by the time, you can see the superior performance of AlphaFold in terms of TM score here. Okay. So next, we look into the application of CNN to other problems. So in this case, it is the counting, detection, and morphometry of cells in the image of a sample. A sample could be some bioassay samples, liquid form of samples wherein there are many different cells, and you want to detect. You can use this electron microscopy, this kind of electron imaging device but still you need to be able to first to determine the type and to count how many of them are in the samples. So this is a typical image image object recognition problem. So you can readily apply image recognition code to this kind of problem. Of course, you need to retrain the AI for the recognition of this specific task. So the particular AI adopted by the authors of this paper is a UNet. UNet is another very, very popular, very, very efficient scene architecture. So apart from ResNet, adopted by AlphaFold. So UNet is also popularly adopted in many publications. So UNet has this kind of structure. You start from initial image and you go through the networks. We know that when we do the convolution, so the feature map becomes smaller in size, smaller and smaller, until it becomes a extended vector. So normally after you arrive this vector, you do this prediction task. But for UNet, it does the opposite. It asks the question, if your vector is so good, can you reproduce the original image? So it goes backward to see whether the derived vectors on the bottom can reproduce the image. So in this process, not only, so in this process, you can actually find a so-called a very good vector for you to do the prediction task. So this is the process prediction task. So this is called this is the UNet model. So based on the this UNet model, according to this paper, it actually performs very well in terms of the counting, detection, morphometry of the cells. Morphometry means you need to be able to recognize the specific morphological feature of the cells. So this kind of thing. Okay, so the next AI model is Raman histology inception. So this is actually a inception model for brain tumor detection. So it actually uses both the image and also Raman spectroscopy to try to detect the brain tumors. So this is particularly useful when you do these operations to cut away the tumor tissues, and you don't want to cut too much because you are dealing with the brain, but you don't want to leave any tumor cells in the brain. It can be you know, essentially it can be fatal, right? So that's why people thought that maybe we can use imaging and spectroscopic technology coupled with AI to do this instantaneous non-invasive detection. Of course, if you do the operation, you already cut the bone and to reach the tissue. So it's already kind of a problem. Anyway, so here we get to know that this so-called inception model. This actually is a more complex inception model. Actually it is a combination of inception and ResNet model. So you can see that in order to achieve a good performance, sometimes you have to use different architectures. Sometimes you have to combine architectures. So this part is a typical inception model. So this is the inception model. Again, for details of inception structure, I recommend you to search the information and to study yourself. Okay. Next application is the is kind of tolerate system for personalized monitoring, monitoring health conditions. Again, using imaging process. Because this is a based on micro essentially the features we can actually see microscopically. So that's why it can use a simple CNN models. Uh, Actually, it's not that too simple as well because it utilizes the inception as well, and then for the detection of the, but it's relatively simple compared to the other tool I just mentioned for this kind of detections. Okay. There's also a publication talking about the learning of the medical images. So you can have so many medical images and very large medical images. If you have a large set of image, and you just like image recognition tasks of human face recognition. It is human face recognition AI is typically trained uh, 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 by at over so actually over 30 over 300,000 images to train a good face recognition AI. So people thought that for medical imaging we should do the same. So that's why some people embark on this kind of a process, using the largest medical image to train a system. But when you do the large image, you have this problem. So, for instance, we look at this image. How do we know if this is a abnormal or normal? Unless doctors, health care specialists, medical specialists, unless they actually mark the image to essentially annotate the image. Otherwise, we do not know. If they annotate the image in colors, then we know whether it is uh, and then we know whether it has a problem, where the problem is, right? But if you have a so large data set, chances are that many of them are not really annotated at all. So that's why we need a pre-training type of model. So that's why this paper is called pre-trained medical image. So UNet is exactly can serve that purpose. We know that a transformer can also serve that purpose, pre-trained models. UNet can also do that. So this is the UNet. So remember that UNet starts from the original image and it learns until you get these vectors. But instead of using this vector for prediction, if you use that vector for prediction, you need to have the annotation. Otherwise, how do you know the right answer? But it can go along this route to regenerate the original image. And then for regenerated image, you don't have to know the annotation. You can simply compare the image pixel and pixel wise. You can make this comparison to see whether it is reproduced 100% or 90%, right? You can do that. So that's why it is a perfect model for pre-training. So this paper actually talked about the development of a pre-trained medical imaging model, and then use a smaller set of annotated data to see if it can actually do this image segmentation. The terminology of image segmentation means that you need to highlight a certain part of the image as some thing, either you need to pay attention or something you think is important, like disease, the section, and so on and so forth. So this is the segmentation task achievable by this pre-trained UNet models. Okay. The next application is a omics AI. Dr. Wang is going to actually go through this AI, the source code of this AI for you, because this is the AI developed by my student. So essentially, it can start with any kind of omics data, transcriptome, proteome, metabolome, and so on and so forth. And then we have a strategy using this manifold embedding strategy to actually convert the complex multi-dimensional data into a two-dimensional image, and then we can apply CNN models to do this diagnosis task to do this biomarker prediction tasks. So this is the AgMap model. So again, it is based on the CNN architecture. CNN architecture. So this is the process. So we start from the initial feature points. For instance, we look into transcriptomic data, gene expression data. So it is the expression of many genes. We use manifold embedding to generate a image feature map, and then we input into this architecture. This is the detailed architecture of AgMapNet. So it is a combination of convolution. You see this convolution, and then you have this max pooling, and then this is the inception. Essentially, it goes several level until it reaches the final output. Okay, so that's all for today. So now is the question time. Uh, let's see if you have some questions to discuss about today's lecture. Okay.
Okay, thank you, Professor.
Mm.
So, first, do you have any question, physical participants?
Mm.
Okay, so we have a first question. That is, he's asking, when passing protein through these processes, do protein not get mutated? It's by Shahzad.
I think that there are some noise, the background noise. So do protein mutation what? Cause some, can you repeat the question?
Okay, he's asking, when passing protein through these processes, do protein not get mutated?
Protein, of course you can deal with mutated proteins, no problem. If a protein is mutated, certainly the local property is changed, and it can also affect the global interactions. For instance, if you can imagine if an amino acid is able to form a hydrogen bond with a remote another residue in remote in sequence but close in geometry. You imagine that if you substitute that amino acid and with the loss of the hydrogen bond, and then it's impossible to form a hydrogen bond, and without that hydrogen bond, so there will be a question of whether the protein fold can be kept stable or not. If not stable, then the protein fold is changed, and then it may affect the functionality. I think there are examples of a single mutation cause the change of the protein structure and then lead to a genetic disease. So I forgot which example, but there is this example, just a single mutation. So of course we don't know, so you can try. I think you can search the internet to try to find that single mutation, and you can try to input the protein, the sequence without that single mutation to see whether AlphaFold is able to give the correct structure. But chances are it may not necessarily because AlphaFold is superior, but because the two protein structures may be already in their training data, so they already know know the answer. So, but we can try. I'm also curious. Frankly, I don't know the answer because I'm not sure whether AI is sensitive enough to just a single mutation. It may or may not be, depending on how severe the property is changed. I think if the property changed significantly, AI should notice that change. If it change only minorly, AI may not pick up the signal. Okay, so that's my thinking.
Okay, thank you. So we have a next question that is by Moni Rao, and she's asking, I hear that Alpha 4.3 has been released. How is it more powerful than Alpha 4.2?
Frankly, I don't know because we have so many different projects here. Actually, protein structure prediction is not my priority, so I have not chased the latest development for quite a while. But I imagine AlphaFold 3 should be at least more powerful than AlphaFold 2, but I really don't know. Presumably, you can search the internet using keyword AlphaFold 3, AlphaFold 2 comparison, so the performance comparison. There should be some performance comparison studies that can answer your question.
Great, thank you, Professor.
Mm.
So today we also have a practical session.
Mm.
And as the last question, that is by Amna Dilshad, and she's saying, what are promising strategies for combining AlphaFold predictions with MD simulations to refine flexible regions?
Yes, AlphaFold. Remember that it is essentially all AI is a statistical theory, so it is based on the training data, and also although it includes many factors like uh, amino acid substitution matrix, like distance matrix, like van der Waals parameters, those kind of things. But certainly there are something, and also all those parameters themselves are based on some studies which may not fully reflect the some kind of true interactions. For instance, what is a hydrophobic interaction? Hydrophobic interaction, based on the the physical reasoning, it is actually a entropic effect, so it can't be easily quantified, let alone you have an accurate distribution. So there's bound to have some errors, some due to statistical treatment, and some is due to the parameters, the limitation of the parameters. So that's why it's better to use alternative approach like a molecular simulation, molecular dynamic simulation, molecular modeling approach to optimize the structure. And even in molecular modeling, there are many different approaches. Even like empirical approach, like MD, right? And even MD, molecular dynamic simulation, there are different sets of parameters. So all of them have some validity in them. All of them has some limitation in them. So that's why it is highly recommended that if you do not reach a satisfactory structure, you think is not the satisfactory one yet, I highly recommend you to try those methods. Particularly, molecular modeling has been around for quite a long time. It's quite established. Uh, just like AlphaFold, molecular dynamic simulation has also won Nobel Prize, right? So they are both established methods. Why not combine them in a more deeper way, in a deeper way for generating good structure? Even in drug discovery, I also suggest that people not only you should use molecular docking, you should also always try, whenever possible, try molecular dynamic simulation to get a better structure for drug-protein interaction, drug-target interactions. Okay.
Okay, thank you, Professor. So we are heading towards the next practical session.
Okay, so
Towards,
I quit.
Professor Wen. Okay, thank you.
Okay, thank you. I quit.
Okay. Hello, Professor Wen. Welcome.
Yeah, I'm here.
Yes, so let's begin the practical session. We are now heading toward the practical sessions.
Okay.
Okay, thank you.
Okay. In the last practical, we have set up a machine learning. And this time, in this practical lesson, we try to set up deep learning. There are three ways to set up deep learning. First, it's use your local CPU. You need to create a new virtual environment and install the CPU version of TensorFlow. And I will show this video.
No need to create a new folder, just go inside that.
So,
as you can see here, I'm
so this time, can you hear the voice?
importing Keras and I'm importing TensorFlow. And when I run this project, I'm getting this error, no module name TensorFlow. So now we will see how we can install TensorFlow and Keras in our Jupyter notebook and how we can run this code. So let's get started. First, I'll create a new folder for my project. I'll call it ML project. And if you already have a project, no need to create a new folder, just go inside that project. Now I'm inside this project folder, hold shift and right click and you will see these options. I'll click on open PowerShell windows here, but if you see an option that says open command prompt here, that will also work the same. Now open your PowerShell window or your command prompt. Now type this command to create a virtual environment. Name your virtual environment anything you want. I'll call it my_VNV. In this virtual environment, we will install TensorFlow and Keras, and we will use this virtual environment as our Jupyter Notebook kernel so that we can use TensorFlow and Keras inside that. Now, if I minimize this and if I reload this, as you can see, the virtual environment is created. Now, on to a very important step, that is to activate the virtual environment before installing anything. So to do that, just type whatever name you had given to your virtual environment, hit tab so that it will autocomplete, write scripts and hit tab to autocomplete again and write activate, hit enter, and now as you can see the virtual environment is activated. Now in this virtual environment we will install whatever we need. So first let's install TensorFlow. Now TensorFlow is installed. Let's now install Keras. So as you can see, Keras is already installed. And now if I go to my Jupyter notebook and I reload this and let's try to run this again, as you can see I'll get the same error because it's still using the old kernel, that is IPY kernel. It's not using this virtual environment in which we have installed our stuff as the kernel. So to do that, what we need to do is we need to install something called IPY kernel in this virtual environment. So type pip install IPY kernel, hit enter and it will install. After IPY kernel is installed, just type python m IPY kernel install -- user -- name and write any name for your kernel. I'll write it ML kernel. Hit enter and now this kernel will be set up to be used in Jupyter notebook. Now if I go back to my file, now there's two things you can do. You can just change kernel in this file, or if I go here and reload, you can create a new file using our newly created kernel, that is ML kernel, and your TensorFlow and Keras will be available. But for now, I'll just reload this again and I'll change the kernel in this file. So click on kernel, click on change kernel and select ML kernel, and after a few seconds it will be setting up. As you can see here, it shows kernel ready, and now if I run this again, as you can see, it is doing the necessary stuff. It is downloading Keras datasets and it will do whatever we have done here in this code. So this is how you can install and run TensorFlow and Keras If you have any questions, let me know in the comments below.
So the second way is use your if you have a local GPU, you can install the GPU version of TensorFlow.
Is that hi everyone, let's go ahead and see how you can install TensorFlow GPU on a Windows computer. You need to come here at tensorflow.org, install pip Windows. Otherwise you can just simply search here, install TensorFlow on Windows. Then you need to open here the first link. You just need to open the first link. Thereafter you need to hide this one and then just scroll it little down, and thereafter you need to select here Windows Native. So in this Windows Native, it says that currently TensorFlow 2.10 or after that, 2.10 or before that is only supported with Windows Native. So with TensorFlow 2.11, it is not supported with Windows as of now, so you cannot install. So basically we have to make sure that we install our TensorFlow less than 2.11. Apart from that, you also need to make sure that you install Python 10 or less than Python 3.10. So whenever you go with Python 3.10, more than the Python 3.10, then it would again start creating a problem. So whenever, if you have installed a latest version of the Anaconda, then probably you might have a higher version of the Python. So you have to create a new environment for your Python 3.10, and then you have to install your TensorFlow and then CUDA toolkit for GPU use. So here I have shown how you can install Anaconda. The link is given in this video description. From there you can watch this video, just see how you can install that. Here is the process which I'm going to show you how you can install Anaconda and how you can install Python 3.10 and then how you can install CUDA toolkit and the TensorFlow. In fact, the Anaconda installation is given in the video, and Python and CUDA, apart from that, the TensorFlow installation is given in this note here. So first of all, you need to create here a new Python environment. So I'm gonna give a name to my Python environment name as PY310. Thereafter you need to open here Anaconda prompt. You just need to search here Anaconda prompt. Just open this Anaconda prompt. Thereafter it will open your Anaconda prompt here. Do not worry, you need to create here first of all a new environment. So I'm just gonna paste that here. Conda create -n py310, that's the Python 3.10 and Python equal to 3.10. So it's going to install Python 3.10 and it's going to create a new environment. It will also install all the necessary libraries needed for your Python 3.10. All right. So here it is installing. It will take a while to install all these necessary packages here. We have to wait for some time. So seems like it has installed all these necessary packages. Now we can activate our Conda package here. So you just need to copy Conda, activate py310. So I just write here Conda, activate Python 310. So Python 310 is now activated. Once Python 310 is activated, thereafter you need to install CUDA toolkit 11.2 and cuDNN 8.1.0. So I'm just gonna copy this whole thing from here and then I'm gonna paste it here. Alright, so this thing is going to install CUDA toolkit and cuDNN in your computer under PY310 environment. So do remember, whenever you need to use your GPU and TensorFlow, you have to make sure that you activate your you activate your environment PY310, so that you can activate with Conda activate PY310. It will take a while to install all these necessary libraries. Thereafter, we will follow here our other steps like Python install TensorFlow. So this will also take a while to install. So let's wait for some time and let it finish first. It has asked me whether you want to proceed or not. Yes, definitely I want to install all the NVIDIA necessary packages in my PC. So it has successfully installed this. So NVIDIA packages are installed. Now we are ready to install here TensorFlow. You just need to copy this and then paste it here. Depending on your internet speed and computer speed, it might take some time to install NVIDIA packages and TensorFlow, because it downloads these softwares from the internet. So obviously, depending on internet speed, it may take some time at your computer. So installation is getting done here. It has downloaded all the necessary packages, which is really quite fast because my internet speed is really super fast. So it took like 10 to 20 seconds for me to only install all these packages here. Once all these packages are installed, then we are going to run our Python, and then we will be testing whether our GPU is working or not. Alright, so in background you can see that it has successfully installed all the necessary packages. Now we are ready to run this code to test if our GPU is working with TensorFlow or not. So you need to just write here Python, and thereafter you just need to paste that here, import TensorFlow as TF. So this is first time, so it will take some time to import TensorFlow. Alright, we are still waiting here. Now you can clearly see here, as soon as I run here this command tf.config.list physical devices, it is saying that there is one GPU available to my computer. Otherwise, you can simply write here tf.test.is GPU available. You just paste it here, and then if you run this, it says that true. That's me NVIDIA GeForce RTX 2060 GPU is available to my PC. So congratulations, you have successfully installed here TensorFlow, and you have also installed NVIDIA toolkit, and you have enabled your TensorFlow to use GPU. Now you can use GPU for a better performance on your deep learning algorithms. Alright, this is all about in this lesson. Thanks a lot for watching this. If you have liked this video, please do subscribe this channel.
Okay, so the last way, if you have a remote GPU server, you can on a local machine. First, on local machine, you need to connect to the remote GPU server using SSH.
Already has with the PowerShell utility, and this. Hey guys, in this video I'm going to show you how you can connect to a remote machine using SSH on your Windows 11 operating system. So for example, I want to connect to a remote server using SSH, and I want to access all the file system or run some commands on that remote server. How can I do it on my Windows operating system? Let's see. So Windows 11 already comes with the PowerShell utility, and this PowerShell already have the SSH client installed. And to check that, you can just search for PowerShell here and then open PowerShell. So just open the PowerShell, for example, and once PowerShell is open, just write this command SSH here and then press enter. And it's going to give you this kind of output, which is usage and then SSH and then it's going to give you some help flags here, which you can use to connect to the remote server. So once you see this kind of output, that means SSH client is already there on your Windows operating system, and you can use PowerShell to connect to any remote server over SSH. Now, for the demonstration purposes, I have this virtual machine set up, and this virtual machine already have OpenSSH server running on it, and I want to connect to this virtual machine using my Windows operating system and access all the file systems and access basically everything in this remote server, right? It can be any remote server in your case. Now, in order to check whether SSH is running on your remote server, the command is really simple. It's sudo systemctl status SSH. Just run this command on your remote server and then give your password. And if it says active running, that means OpenSSH server is running on that server, and you can connect to this remote server over SSH. Now, in order to connect to this virtual machine, let me clear the terminal. You just need to know the username and IP address of your remote machine and hopefully the password to log into your machine, right? So the username here is CodeBind in my case. Just know the username of your remote machine, right? In order to know the IP address, for this demonstration, I can give if config command here, because this is just a virtual machine running locally on my system, right? So you can see this is the IP address right now. So I can just connect to this virtual machine using this IP address. In your case, it can be the IP address or the host name of your remote machine. So I know the IP address, I know the username, and I also know the password of this remote operating system. Then on your PowerShell, you just need to give this command. Just write SSH and then the username. In my case, as I said, username is CodeBind. So I'm going to give the username here. @IP address. So in my case, the remote machine's IP address is this. So I'm going to give this IP address, which is 192.168.152.128. And then my OpenSSH server is running on the default port, which is 22. The default port for OpenSSH is 22. If this default port is different on your remote server, then you can give -p and then the port number of that remote server, right? In my case, I don't need to give any IP address because I'm running OpenSSH server on this virtual machine on the default port, which is 22. You can also give 22, which is essentially going to connect to port 22. But if you don't give this -p22 command also, it will work, right? I will press enter here, and then you will see this kind of output which says the authority of host this can't be established. Key fingerprint is this one. This key is not known by any other names. Are you sure you want to continue connecting? I just need to type yes here and then press enter, which is going to ask me for my virtual machine or remote server's password, right? So you need to give the password of this remote machine, which you use to log into your remote machine. So let me give that password and then press enter. And I think I just typed wrong password. So let me retry again. And then this time hopefully it works, and it works. You see, now I can see username is CodeBind, which is same here, right? So now I'm connected remotely to my remote operating system over SSH. So let's try something. So let me clear the terminal here. Let me clear the terminal here also. And if I do ls here, I will see similar kind of outputs or similar kind of folders and files, which I will see here when I try to give ls command here, right? So you can see all files and folders are same as my remote machine. So essentially what I'm doing here is I'm just accessing this remote machine over SSH in this PowerShell, right? So everything you see on your remote machine, you will have the access to that in your SSH connection, right? So now you can do any task, or you can perform any command in this PowerShell, and it will run on your remote system. So that's how you can connect to a remote server or remote machine over SSH using Windows 11. I hope you enjoyed this video, and I will see you in
and then on the remote GPU server, you need to install Anaconda, create a new virtual environment, and install the GPU version of TensorFlow. It's basically the same as we did on Windows. And the last step, you need to set up Jupyter on the remote server and connect it from the local machine, so we can code in our browser.
the next video.
This is the IP. So don't know yet. So in this tutorial, I'm gonna let you know like how you can access Jupyter Notebook from the server. So let's get started. So suppose this is your command prompt, or you can say like the server in which you are currently. This is my server. I'm using actually Raspberry Pi. You can be in AWS or whatever. So if you like, you first have to know the IP address. If you already know the IP address, then that is well and okay. And if you don't know, you just type ifconfig on the server command prompt. So yeah, so you can see this is the IP. So I have to say inet. You can see this is the IP. So I have just copied the IP. If you already know, so that's well and good. So let me just sticky notes, copy it. Yeah. Yeah, let me just paste it here. Okay, this is the IP of the server. So let me just clear it. So first install pip 3 install Jupyter Notebook dash you get because if you have installed, then it's okay. If you haven't, so like install like this. So I have already installed, so it will say requirement satisfied. So now for making it public, your like Jupyter Notebooks, just run like Jupyter Notebook dash IP space 0.0.0.0. So after that, like that dash IP, then you say 0.0.0. So basically you are telling, okay, it will be accessible from everywhere. So you are telling, sorry, it just, okay, let me just, yeah, so you are telling to let it be accessible for everywhere. So just run it. Okay, it's running. Okay, see, it's running now. So this is the like IP address. Like I'll tell you like how to access from the browser. And one more thing, let me just end it. So sometimes it doesn't run like from this command. Then you have to type this command like Python 3 m dash m like flag m notebook. If above command doesn't run, then you have to run this command. But 99% above command will run. So Python 3 minus m notebook dash IP 0.0.0. So see, this is also running, this is also, both are the same thing. Okay, so if above one doesn't work, you just run this command. So now this is the IP address I have told you. So just copy the IP address and just paste it here And on this, you can see it's running on the port 8888. It may be different on your device, but default port is 4 times 8. So just put like this and do 8888. So let me just show you in the bigger what's the IP I'm putting. So I'm putting this. It's not getting bigger. Okay. Yeah. So this is the this is the IP address. Then two, like whatever you call, I just forget its name. Then 4 times 8. So, yeah. So let's just enter it. So it's asking for password or token. Now go back to your kernel or whatever. See, you can see this is the token. After equal to, it might be token equal to. Just copy that token and click the right click. Okay. Now token has been copied. Just come here and paste it and log in. And see, it's running. And it's perfectly running. You just have to give token at only one time. After that, you can just do like 100 times. It won't ask. So now you can just make like new Python 3 notebook and start working on it. So yeah, that's for all. But it works slow on the server as compared to on your own machine. So it was all from my side. Thank you.
Okay, that's it.
Okay, thank you, Professor Wang. Thank you for the lecture. So when will be our next practical session? Professor, are you hearing me?
When will be our next practical session?
Okay, thank you, Professor.
Thank you.
Okay, bye-bye.
Bye bye.